Hi everyone. Okay, let's try reloading that. Oh, that's not working. Okay, that's fine. It's not so important. So I'm just gonna go over the worksheet from today's class. I wasn't in class today, so if there's stuff that is repetition from things we did in class or anything like that, just know that that's unintentional. I just had to miss class today, unfortunately. So this is our first statement. Oh, the one thing that I wanted to show you guys in the lecture is just like a mnemonic device that I like to use. We have these two symbols, and sometimes people confuse them. And this looks like a backwards E. So this one is there exists, and the word exists starts with the letter E. And this looks like an upside down A, and this means for all. And these are going to come up all the time. And we're going to be using them today, I think. So that's just something that I like to do. And sometimes people say for every, which is really confusing because then they both start with an E, every and exists. But I like to say for all, especially when I could catch myself. But you might catch myself saying for every at some point. But I'll try to say for all because I think that mnemonic device is kind of helpful, and at least until it becomes second nature. Okay, so here we have to write the following statement in symbolic language. If any of you guys know other languages or have learned other languages recently, you know that it's always easier to go from the foreign language to your more natural language than it is to go like from, let's say if you're a native English speaker, it's harder to translate from English into the other language. It's like easier to understand a foreign language than it is to construct language in it. So this exercise is actually kind of difficult sometimes. So we have the product of an even integer with any integer is even. And this is kind of like intuitively true, I think. If we multiply anything by an even integer, any integer by an even integer, it's going to be even. And you could run through a bunch of examples in your head. And the question is, how do we write this? And there's a really easy way of writing it that I'll just show you real quick, which is for every x that's even. This is not the answer to the question, by the way. I'm just showing you, like, if we didn't have all this instruction up here and we just had to translate this into a statement, then we could do it like this. For every y, you should be able to guess what I'm going to say here. For every y that is, what's the constraint on this? It has to be an integer. We already said that x is the even integer and y is just an arbitrary integer. Their product, so x times y, is where? Belongs to the set of even integers. So that would be equivalent to this statement. Now, we're told that we need to write this as a direct implication. And this is what makes it a little bit more challenging because implications are not always so intuitive. I figured out how to erase on here. So we're getting a little better. So in order to do an implication, you sort of have to have two statements. You have to have this like premise or process and a conclusion. And so here, our conclusion is clearly that the product is even. And our premise is sort of the building blocks that get us to that conclusion. So let me just make sure this is recording. Okay, I think that means it's recording. Our process is that we have an even integer and any integer. So it's going to be kind of similar to what I just showed you, but here we're going to have like x is in the set of even integers. I don't even need that. And we need both these things to be true. Y is in the set of any integers, all integers, whatever. That being true, that's our premise or our process. That implies the conclusion that xy, or x times y, is in the set of even integers. And here we have an implication. Cool. Okay. So that is like the answer to the first part of our problem. And now you'll probably see when Professor Carbone posts the solutions that she does an equivalent form of this as not P or Q. And this is the complicated part. And I don't think we did truth tables today because I looked through the lecture and there was nothing about truth tables. And I'm going to kind of give you a quick intuition, or I'm going to try to give you a quick intuition onto how implications work. This was very hard for me to grasp as a student, and it's not intuitive. But just know, this might even be something that I recommend you memorize, because I don't think it's so intuitive. Would be that implication. Another form of writing this implication is not P or Q. And that is written in the worksheet solutions. But again, I wasn't in class today, so I don't know if this was explained. Not P or Q, where P is our premise or our process, and Q is our conclusion over here. Now, why is this equivalent to this implication? So here's the intuition that I would say. Let's say our premise is true. Let's say we're premising our belief on the fact that like 2 is an even number, or the earth is a sphere, or something like that. It's not flat. Some true statement should lead us to another true statement. When we start with a true statement, we should be able to end with a true statement. But if we start with an untrue statement, if our initial belief is not true, not P, so our initial belief is false, we could go anywhere. We could accidentally stumble upon this true conclusion, which would be, I guess, lucky. Or we could stumble upon a not true conclusion, which is more likely. And both of those could be internally logically consistent. If we start with bad data, we're going to end with a bad conclusion. Or sometimes we might get lucky and we might end on a good conclusion. But either of those cases can happen and are reasonable. The only case that's not reasonable is if we start with good information, P, and we end with some false conclusion. That means something went horribly wrong. And so that is the only case where the implication is false. If we start with something that's false, no matter where we end, it could make sense, you know? But if we start with something true and end with something false, that's bad. That's not what we want. So the only time an implication is false is when we have P and not Q, when we have this case, which means that the inverse of that is when implications are true. When we have not P, notice this is the case where we have not P, and it doesn't matter what Q is. And here we have the case where we have Q. So this over here encompasses all of these cases where implications are true. And if this is not so clear to you right now, that's okay, because I think we're going to be delving into this a lot more next class and maybe the class after that. So if this is still kind of fuzzy, think of this as just like a little bit extra, and you don't need to fully understand this yet. But it's important for this problem because the next thing we need to do is negate this statement. I'm still erasing. And in order to negate, we need to use this kind of form, because the opposite of this is, actually negating this is super easy. First, we're going to negate not P, which becomes P. Then we're going to negate the or, which becomes and then we're going to negate the Q, which becomes not Q. So we're just doing like this stepwise negation, and this is always going to work. And so it's actually really easy to figure out the negation of this kind of thing. And remember, this is our P, and this is our Q. So what we have to do here is take this and negate it. So we're going to say x does not belong to the evens. Another way of saying this is that x belongs to the odds, but I prefer this because it's more direct. And then we're changing the and to an or. we're just doing the stepwise negation. Or y is not an integer. And remember, here we're not using this implication arrow anymore. We changed it to an and. Oh, I made a mistake. I'm sorry. I was rewriting this as not p. Yeah, so we want... Let me redo this. We want p and not q for our negation. I was sort of writing the equivalent form. If you want to see the equivalent form, that'll be in the worksheet solutions. But I'm just going to go straight to the negation for the sake of time, because I already know I'm being long-winded here. So p we're copying directly from here because this is p implies q. I should write that. P. Oh, how did that happen? I don't want to fill. Where did I go wrong? Maybe I do white fill. That should save it. Okay. P. This is also disgusting. Okay. P implies. There we go. P implies Q. That's what this is. So we're keeping our P, which is X is even. And Y is an integer. And not Q. And XY is not even. Or you could say XY is odd. Both are correct. And we could see how this is a negation. This is the opposite of our initial statement, basically. That our initial statement said that this premise, that x is even and y is an integer, means that xy is even. And here we're saying, actually no, x is even and y is an integer, just like we said before, but also xy is not even. And this statement happens to be false. And now lastly, so that's the negation. The last thing we need to do is called the contrapositive. And let's just erase a little bit. Okay, I'm going to get rid of that. The contrapositive is kind of what you think of as the opposite. So P implies Q. We're going to reverse the order and change the symbols. So we're going to say contrapositive means that not Q implies not P. So a way of thinking about this in our example is that we said that x being even and y being an integer implies it means that x times y has to be even. Now, an alternative way of saying this, kind of in a backwards form, is that if xy is odd, if it's not even, so that part's not true, that means that at least one of these things has to not be true. Something here doesn't hold if this doesn't hold. This process is holding up this conclusion. So if this conclusion falls, that means something in the process went wrong. I think that's like a good English way of thinking about it. These are the support beams, and that's the building. The building fell. One of the support beams must have wavered, at least one of them. So not Q means that xy is not even. And that implies not P. And so this is the same thing where we're going to invert. We're going to do the opposite of P. So either x is not even, or we're changing the and to an or because we have not P instead of P. Or, and you should be able to finish this sentence, y is not an integer. Whew. All right. That was a lot. So now let's get rid of everything and move on to question 2. And yeah, hopefully this is helpful for you guys. So now, let me see. Oh, I have an issue here. When I tried putting the text over the erased stuff, I guess the eraser doesn't actually get rid of everything. It just, could I do that? Oh gosh. What's gonna happen if I go all the way back? New, fancy text. Let's try this. I have a good feeling. Yes. Ha. That's so cool. And then n+1. Okay. So we're still learning how to use this technology. We don't want fill. This is what we've learned. So we don't want fill, but we want outline, and we want it in black. Let's see. No, that's weird. I just want it in black. Is that so hard? Yeah. Perfect. Okay, so write the following statement in symbolic language. Determine suitable methods of proof. Given any pair of... Okay, so here's the statement. That's where the statement starts. Given any pair of consecutive integers n and n+1, exactly one of them must be even. This is a very precise statement. It's not that they are even. It's not that they are not even. It has to be 1. So how would I think about this? Any pair of consecutive integers n and n+1. So we have to have an n. n+1 depends on n. So you almost don't need to declare it by itself. So you could almost just say for any integer n, for all, right? We're doing the upside down a for all n. And what's the constraint on n? What universe does it belong to? Integers. So it belongs to the world of integers. For all the integers. Now the statement is that one of n or n+1 is even. So you're tempted to say this. You're tempted to say n is even. This is good, actually. I like this problem. So n is even, or, right? That's the v for or. n+1 is even. And hopefully you guys are getting a little bit more comfortable like using these universes, like z is for integers, e is for even, n is for the natural numbers, stuff like that. Hopefully that's starting to get integrated into your knowledge. So even if you're struggling with this new material, like you guys are coming a long way. And this is stuff that probably wasn't easy for you on day 1, and hopefully it's getting easier. The fact that this v means or, hopefully that's also getting easier for you to not have to keep reminding yourselves of. So n is even or n+1 is even. So now just think for a second, what's the problem with this? So maybe you pause the video or not. Either way, there was something very important here. It says exactly 1. And we talked a couple classes ago about how we use an inclusive or. So when we say n is even or n+1 is even, implicitly in this is that n and n+1 are both even, would also satisfy this statement. If n is even and n+1 is even, this statement would be true. And that's the problem. We don't want that to be the case. We have to make sure they're not both true. So we also have to say not n is even and n+1 is even. And is the upside down v. n+1 is even. Okay, so that's our statement. And now I'm just gonna look over. Yeah, okay. So I think I looked through kind of the solutions on the worksheet, and I think the solution that is the easiest, or the one that I would have thought to do, is a proof by cases. And this talks about what it means for a number to be even. So there are multiple ways to prove this, and there's probably also multiple ways to write this out and that are correct. So don't worry if you came up with a slightly different way of writing this, it's very possible that it's correct. So a proof by cases. A proof by cases means that either let's start with n being even, or let's start with n plus 1 being even. And we'll make sure, am I saying this right? 1 second. Okay, so here's how I want to do this. We know that n is an integer. Now, all integers are either even or odd. So let's just look at the case where n is even. If n is even, that means another way of saying an even number. This is very important, and I talked about this in the last video, so if you didn't get a chance to watch that, highly recommend it. It's not quite as well done, hopefully, as this one will be, but I do talk about like what it means for a number to be even or odd. An even number is divisible by 2, so that means that n equals like 2 times a, where a is an integer. Integer means that it's in the set of Z, that's its universe. So n is divisible by 2. That's basically what I'm saying here. And that is the same as saying n is even. Now if n equals 2a, and it's even, that means that n plus 1 equals 2a plus 1. And we actually learned that 2a plus 1 is how you would construct an arbitrary odd integer, where a is again an integer. Important to remember to write that. So we could go into a proof of this, and the way you might prove it is by dividing 2a plus 1 by 2, and you get a plus a half, and you know that a plus a half is not an integer because a is an integer. And if you add a half to any integer, you're going to get a non-integer. So you could go about proving that, and it's not very hard, but I don't think we're going to require you to prove that, because we've already constructed this idea that all odd numbers take the form 2a plus 1. So if you just write this is odd, as we have shown in class, I think that will be enough. So here we just looked at the case where n was even, right? One of the two cases, either n is odd or n is even. We started with the case where n is even. We saw that obviously n is even, which we established at the beginning, and that also means that n plus 1 is odd. So here we have a case where we took consecutive integers and exactly one of them was even. Now let's look at the case where n is odd. And what we're hoping to see, so here, case 2, here n is odd. This is the alternative case. And what we're hoping to see is that n is odd implies that n plus 1 is even. We want to show that n plus 1 will be even here so that we have another case where we have two consecutive integers and exactly one of them is even and the other one is odd. And that's what this statement says. So that's what we're trying to prove. So n is odd means that n takes the form of 2, this time I'll use b. It's always good to change variables when you're doing a proof. 2b plus 1, where, what do we have to say? That b is an integer. We have to be very precise with our statements, because if b is like pi, then none of this would make any sense. N plus 1 is not going to be even or odd, n is not even or odd because neither of them are integers. So we need to make sure we're staying in the correct domains, in the correct worlds. So that implies that n plus 1, we're just adding 1 to both sides here, is 2b plus, equals 2b plus 2. And we could prove that this is even. And we could say n plus 1 equals 2b plus 2. N plus 1 is just some number. And to prove that a number is even, you have to show that when you divide it by 2, it is an integer. And so I'm just going to kind of go shorthand on this. But if we do 2b plus 2 divided by 2, we end up with b plus 1. And how do we know if b plus 1 is an integer? So the way we would know that is that b is an integer. And if you add an integer to any other integer, that's also an integer. And b plus 1, so therefore b plus 1 is an integer. And n plus 1 is therefore even, because it's divisible by 2. We divided it by 2, we got an integer, therefore it's divisible by 2, and therefore it is even. So we've just shown that if n is odd, n plus 1 is even, and if n is even, n plus 1 is odd. And it seems very obvious that that's the case, because we know how to count, and we know that integers rotate between even, odd as you count up. We still have to learn how to prove these things, and we still have to learn how to write these things out. So that was kind of the point of all this, and hopefully this was helpful for you guys. Let me or Arya know if you have any questions. I understand this is going to be broadcast also, or available also to the other section that Professor Carbone teaches. So I'm sure if you guys have questions for your LA or Professor Carbone, that's also great. Have a good day, everyone.